Hey guys, the lecture I have for you today is 6.5 in AP Chemistry, which is energy of phase changes. This whole lecture is all about how energy is transferred when materials are going between solid, liquid, and gas, and also when they're going backwards from gas, liquid to solid. So let's just go ahead and jump right into it. Again, these are all the things that you're expected to do by the end of Unit 6. So you can read over those. You can pause this if you want to, just as things you should be able to do related to this topic. So I think it's actually best to start this unit off with a question. And the question I have here is, how much energy is required to heat up 10 grams of ice at 0 degrees Celsius to water at 100 degrees Celsius? So I asked this question because if you're in my AP Chemistry class, in our last lecture I introduced this equation. I introduced the equation Q equals mc delta T, or what we call the Q equals MCAT equation. And the Q stands for heat, how much heat is gained or lost in a reaction. M stands for mass, the amount of grams that you have. C stands for the specific heat capacity, so the amount of energy it takes to heat something up. The higher that is, the harder it is to heat you up. The lower that is, the easier it is. And then delta T is just your change in temperature. So how much energy is required to heat up 10 grams of ice at 0 degrees Celsius to water at 100 degrees Celsius? And if you were trying to attack this problem, just like I taught in the last lecture, what you would probably do is you would say, okay, I can figure this out. Well, I'm looking for energy, so that's going to be my Q because heat is energy. And so I've got 10 grams of ice. Well, if you remember from last lecture, the specific heat capacity of water is 4.18 joules per gram per degree Celsius. And I multiply that by, well, my delta T, my change in temperature, I'm going from 0 to 100, so my change would be 100 degrees Celsius. And you can take that and you can plug that into this equation, do it in the calculator, and what you'll come out to, if I've done my math correctly, and I think I have, is 4,180 joules would be required, okay? That's what you might think the answer to this is. But that's not actually the correct answer. The correct answer to this is to go from ice at 0 to water at 100. The correct answer is actually 7,510 joules. And so the question I want to raise with this is why? Why does that equation fail? What are we missing from this lecture, from last lecture, that could actually get us to that number? And what we're missing is how energy is actually transferred to molecules, to compounds, to go from solid to liquid, okay? When you give heat to a solid and you start heating it up, so you start melting it, there's actually two different ways that the heat can be transferred, okay? One, you can give the heat to the molecule, you can give the heat to the compound to increase its kinetic energy. In other words, how fast it's moving, how fast it's translating, vibrating, rotating. That's one way that you can do that. When you're increasing the temperature that way, you're increasing it, giving the kinetic energy to it, you use the MCAT equation. But there's another thing that can happen when you are trying to melt, when you're trying to vaporize, and that is the energy is not going to raise the temperature. The energy is actually going to break intermolecular bonds. So you can give energy where all the molecules are now speeding up as you're giving them more energy. But one thing you've also got to do, like for example, if you had water, you actually have to break those hydrogen bonds. You have to get those water molecules away from one another as you're melting and as you're vaporizing. So sometimes when we give heat to things, we're not increasing the temperature. What we're doing is we're trying to get the molecules apart from one another, right? So let's think about this phase change diagram. Now I introduced these guys in the last diagram. Think about what's going on. So let's look at the phase diagram. Let's try to orient ourselves to what's going on there. The y-axis is degrees Celsius. The x-axis is heat absorbed. So I'm giving heat to some substance, and the temperature is going up in some places, and in some places it looks like it's staying flat. And the question is why? Well, hopefully with that last slide, that kind of answered part of that question. So what's happening to the temperature in regions A, C, and E, I think you guys can figure that out. So what's happening there? Well, it's going up, right? As the heat's being absorbed in region A, So let me get my pointer here. As the heat's going up in region A, or we're giving heat to it, the temperature is also going up. As we're giving heat to C, the temperature is going up. And as we're giving heat here at region E, temperature is also going up. So what's happening to the average speed of the H2O molecules? Well, I've taught before in my lectures that temperature is a measure of average kinetic energy. And average kinetic energy helps you measure speed. So if the temperature is going up, the average kinetic energy is going up. And if the average kinetic energy is going up, then your speed is going up. So what's happening at regions A, C, and E? Well, we are increasing the average kinetic energy, so we're increasing the speed. And then what is the heat energy supplied doing? Well, the heat energy supplied is increasing my average kinetic energy. It's increasing my temperature. That's why as I give the heat here, it is increasing on my graph. I think that's pretty self-explanatory. Regions B and D, though, get a little bit more tricky if you've never seen one of these diagrams before. So what two things might cause the energy required to differ? So what does it mean by that? Look at region B right here, and then look at region D. You see how the amount of heat for B is so much less than the amount for D? Well, what's going on here? Well, if we start down here and imagine this is water, down here our water is ice. It's solid. And then we heat it up, heat it up, heat it up. Well, what's happening at B? Well, at B, we're melting. What's happening right here is we're melting, okay? So the intermolecular forces, so I got my molecules and they're kind of vibrating as a solid. We give it more heat, and now they can more freely flow as a liquid. So we didn't break hydrogen bonds necessarily, but we moved our molecules apart a little bit, okay? And so at B, I'm kind of starting to break those intermolecular forces between them. And so all the energy is going to kind of separating my molecules and allowing them to move freely, right? Well, then once they're all freely moving, once we've got them all as a liquid, then they can heat themselves up. And so when they heat themselves up right here, we're heating, going from 0 to 100. And when we get to 100, well, that's the boiling point of water. So what's happening right here? We are boiling. We're vaporizing the water. And so at this point in time, the energy is not going to raising the temperature. The energy is going to taking those water molecules and separating them so they can now be a gas. They can all bounce all over the place. Okay? So why in the world is the energy different between B and D? Well, in B, we're going from a solid to now a liquid where we're just kind of rotating around one another. Yeah, they moved apart from one another, but not very much. So it didn't take much energy to just kind of barely move them apart. But at point D, I'm taking my water molecules and I'm completely separating them from one another. And so it takes a lot more energy to separate them completely than it does to just separate them a little bit. So it takes more energy to boil something than it does to melt something. What's happening to the temperature? Well, I hope you can see this. At B and D, it's completely constant. Weird thing, if you go take a pot of water and you boil it and you put a thermometer in it, you'll see it never changes from 100 degrees Celsius. The temperature stays constant as you're boiling it the whole time. So the temperature doesn't change during a phase change like melting or boiling. What's happening to the average speed of the H2O molecules? Well, if you think about this, temperature is a measure of average kinetic energy. Well, since the temperature is not going up, or the temperature is not going down, my average kinetic energy is not changing. And because my average kinetic energy is not changing, my speed's not changing. So what's happening to the average speed? Not a thing. It's staying constant. And then what is the heat energy supplied doing? It's trying to break those intermolecular forces between them. That's what's happening in regions B and D. The intermolecular forces are breaking apart. So again, this right here just kind of goes over this, what I just went over. If you want to take a second and you want to pause this, look at it again, read my explanations over here, please do so. There's not really much more to explain here other than at the regions where we're going up, the kinetic energy is increasing, the temperature is increasing. In the regions where we're flat, we're doing a phase change. The kinetic energy is not increasing, the potential energy is increasing because the distance between my molecules is changing. One other thing, so to get into why at the beginning we calculated the 4,100 and 80 is what we thought was the answer, joules to turn 0 degrees Celsius to 100 degrees Celsius for water going from ice to liquid. We said that was wrong, and we said in reality it was 7,510. Well, why is that? Because there's another equation I haven't taught you yet. There's another equation you haven't gotten to yet, and that's this guy right here. This equation has to be used when you're at a phase change, because the original equation, the Q equals MCAT, has a delta T term in it. In other words, a change in temperature. Well, at a phase change, there is no change in temperature. So you can't use this equation. Doesn't work. Okay? But at a phase change, we use this equation, Q equals M delta H. So Q is the heat, just like it is in the Q equals MCAT equation. Delta H right there is a new thing. It's called the enthalpy of phase change. Okay, it's the enthalpy for the phase change. So it's the heat of blank or molar heat of blank. There's two different ones you can have. You can have a delta H of FUS. You'll see that. That's called delta H of fusion. That is used when you are melting or freezing. Okay, so melting / freezing. Okay. The other one that you can have is delta H vaporization, and that's happening, because this is vaporization. My handwriting's terrible. And that's happening when you're boiling. Right? That happens when you're boiling. Okay? So you have to use a different delta H depending on whether you're boiling or whether you are melting, freezing. Okay? The M, just like in Q equals MCAT, is still mass. But you'll see that there's another equation. We can also do this sometimes with moles. And we'll do a couple of examples right now. So let's do this one first. It says, given the heating curve for mercury, calculate the heat to freeze 100 grams of mercury at its melting point. Okay? So if I come over to the graph, I'm going to notice that this is the melting point right here. Okay? That's my melting point, 234 Kelvin, right? And what it tells me is the heat of fusion. Okay, the heat of fusion right here. The delta H of fusion. That guy right there is equal to 2.30 kilojoules per mole. Okay? So that's the information I got so far. It wants to know you're at the melting point. You are already at the melting point. Okay? How much energy is going to be required, or how much energy is going to be let off to freeze 100 grams of mercury? Well, something I want you to notice is that this guy right here is moles, which means I'm going to have to change the grams of mercury to moles of mercury to start off. So if I go look at a periodic table, I would find that 100 grams of mercury times 200.59 grams of mercury for every 1 mole of mercury, my grams would cancel. That would tell me I'm roughly 0.5 moles of mercury. Roughly. It's really 0.499, but close enough. And sometimes in AP Chemistry, you want to do things just fast. You've got the idea behind it. Do it quickly, especially on like a multiple choice exam. 0.49 and 0.5 are not going to give you that different of an answer for things. So, round things where you can sometimes. And so I'm now going to plug this into my new equation, my equation that is Q equals N delta H, because I was given moles and I was given a delta H of fusion. So that's going to be equal to 0.5 moles times 2.30 kilojoules per mole. Moles cancel. And if I do the calculation for that, so if I just get a calculator for that, I get roughly half of 2.3. So that would be 1.15 kilojoules. Now, the question is, what's the sign on it? Okay, is the sign going to be positive? In other words, did we take in energy, or is it going to be negative? Did we lose energy? And if you are freezing, we talked about in past lectures, freezing is an exothermic process, which means we are going to lose 1.15 kilojoules. Okay, so hopefully that makes sense. Rewind it. Ask me questions in the comments if that doesn't make a whole lot of sense. I'm going to leave you with one other question for you to try to solve yourself. So here's the question right here. For those of you that are in my class, going ahead and try to solve this on your own. See if you can figure out the correct answer to this. For those of you that aren't in my class and are just watching the video to try to learn a little bit more about AP Chemistry, go on ahead and solve that. And then if you want to know what the answer to it is, I'm happy to leave that down in the comments. So just ask me. But hopefully all that made sense. Hopefully it wasn't too much for this lecture. But just let me know what questions you have down in the comments, and I'll do my absolute best to get back to them. So thank you guys for watching, and I'll see you guys next time.